Okay, thanks for the invitation and thanks to all the organizers for all the getting us all together here. Nothing like a bit of mathematics to wake you up in the mornings. So I'd like to first just acknowledge my collaborators, Lanjing Bao, who's actually done the lion's share of the work on this problem, Igor Belik, her supervisor at Georgia State, and of course, PI on our grant, Daniel Yurchenko. Okay, so I'm going to talk about global dynamics, which there's not a lot of in non-smooth systems. But let me just tell you the motivation for this, which we'll come back to this again and again. I won't talk a lot about energy, but we're motivated by this model of an energy harvester based on an impact pair, meaning we have a cylinder that's being forced harmonically, a bowl inside of that cylinder, and it's impacting either end of the cylinder, which has dielectric polymers on either end, which can be stretched. Oops, wrong button. Stretched, no, still the wrong button. Yeah. As shown here, with a capacitance change that you can actually harvest energy. And so for our purposes, we're going to basically focus on the fact that when we harvest energy, it's going to be quadratically proportional to the relative impact velocity. So we'll be tracking relative impact velocity most of the time. Okay, so I'm going to mostly stick with the basic model of an impact pair. So we have this forced cylinder. This is our cylinder being harmonically forced. The ball's in there. We can actually tip it, so some gravity could affect the ball movement, but otherwise the ball is driven by impacts. And so we have this impact condition for the ball with a restitution coefficient R. We neglect the mass of the ball relative to the cylinder, so that simplifies our impact conditions considerably, and it's also instantaneous, so we don't have any compliant model or something like that for the impact. So it's just keeping it very simple. All right, so in that setting, we could model, we could just track the cylinder, which is oscillating with, as you can see here with the blue lines, with the ball bouncing back and forth inside with the red line. But we actually moved to the relative displacement, relative coordinates. Makes sense since we're interested in relative velocity anyway for the energy. So that will just fix the boundaries. And here you can see it in the time series or in the phase plane of the relative velocity versus the relative displacement here, Z. We'll track for that. So we have our equations of motion for Z. It actually collapses down to this one equation with the forcing. And then our impact condition also simplifies down considerably with the just the R here, change in velocity as we have impacts. Okay. So the one thing we've studied a lot of the bifurcation sequences. So this is what I'm not going to talk about today, but just to show you a little bit of that, it motivates what I will talk about. So we can get all sorts of different behavior. We can get this just regular back and forth behavior, again, showing in the phase plane or in the time series, just hitting here we'll note the bottom and the top of the cylinder. So moving back and forth between impacts. We can get period doubling. We can get chaotic behavior where it's still just moving back and forth, but in a chaotic way. But then we can get additional impacts. So here we have impact velocity versus our dimensional, a non-dimensional length here, D. And we can get all sorts of bifurcation sequences in terms of that. Let me just say that D, okay, it's a non-dimensional length. It involves either the dimensional length or the amplitude of the forcing. So it's kind of this combined non-dimensional variable. But anyway, so the point is we can have multiple impacts on one side. So we have these sequences will hit twice on the bottom and once on the top. We can have unstable branches of those, fold bifurcations in those. And then, of course, various sequences of grazing bifurcations where we add further and further impacts on one particular side of the cylinder. Okay, so as I said, I'm not really going to talk about that so much today, but the what goes into the studying the bifurcations are essentially maps, right? That map from let's say, the bottom to the top of the cylinder and back again. Or we can also map, let's say, impacts that just hit twice on the bottom or twice on the top. And so any sequence can be just broken down into going from bottom to top or staying on one side. So we could have, here we just use a notation. So N impacts on the bottom, M on the top. And that could just be the sequence of P1, P2, and so on and so forth to get the right impacting sequence. And so our very simple periodic case where we just have one impact going back and forth on the bottom of the top will just be P2 composed with P3. Multiple impacts on one side will have three of these maps combined. We could have chaotic sequences, which will be just some collection of these maps and so on. Okay, so as I said, I'm not going to talk about those maps so much, but I do want to mention that these have, of course, implications for energy. So as I mentioned, we have these bifurcations from where we just have our simple bottom to top impact sequence. Then we can go to where we have what we call two impacts on the bottom, one on the top. And that has implications if we look at the harvested energy. So just focusing in, for example, in this little region here, the blue and the green are just the impacts on the energy from the top or the bottom. But the red here is the mean energy, all right? And we could look at mean energy per time or mean energy per impact. And so if it's mean energy for impact, we'll actually have a jump down if we're going to the 2-1 case through a grazing bifurcation. Or it could go up if we're looking at mean energy over time interval. And that's really because this second impact on the bottom has small impact velocity, so it could add over time, but on an average, it'll bring our average down, right? But in any case, whatever we're interested in, we will have a jump in this energy. We actually care about these types of bifurcations. Okay, so just to mention, I mean, I'm looking at, in some sense, the simplest example of an impact pair kind of stripped down version. There's many models for this, microactuators, gears, a lot in the Vibro-impact energy transfer literature in terms of a nonlinear energy sink. And then there's also, various types of analyses in impact pairs, in terms of these maps, bifurcations. I think there might be some interesting connections with Yang's talk yesterday. And then there's also some very analytical work on just analysis of non-smooth maps with the impact pair in the background. Okay, so just to give you a sense that, I mean, these models do show up pretty regularly. Okay, so the whole point, though, is let's talk about global analysis. So what I've shown you so far is essentially local analysis, right? Following different bifurcation branches that, then we look at their stability or, different sorts of changes. And as was already mentioned yesterday, right, we can get classical bifurcations, we can get non-smooth grazing bifurcations, and so on. We can track unstable grazing and so on and so forth. But what we're really interested in at the end of the day, from the energy point of view, is the regions of attraction for our relative impact velocity, that gives us our energy, as well as our impact phase. So in order to look at the solutions of these problems, actually, maybe I mentioned it back here, yeah. When we look at the solutions for these maps to characterize our solutions, we can't just get impact velocity because, of course, this is a non-autonomous system. So we need second variable, let's say, that characterizes our solution, impact time, or we'll actually look at impact phase, meaning just how out of phase the impact is with the actual forcing of the cylinder. Okay, so we're really interested in, where do these things live, because that actually tells us what sort of energy we're going to be producing. And as has already been sort of noted, I didn't point it out so much, but there's bistability also that can show up in many different ways. Here we saw a little bit of that with the it is actually bistability between 2-1 and 1-1 type solutions. But we can also have windows of chaos. I mean, these are just two different bifurcations for different parameter combinations. So that's also brings up questions of where does our impact velocity live in terms of giving us a particular type of energy. Okay, so that's why we're kind of interested in the global case. And in particular, let me just dig a little bit into this bistability example. So just zooming in on this bifurcation figure I showed earlier, we have these 2-1 or bottom, top, and bottom, top alternating impact sequences. There's a fold bifurcation for the 2-1, so that's why we end up with this bistability. And we can see the bistability if we just do continuation of course, this is our bifurcation for the impact velocity. If we decrease our d non-dimensional length, follow that branch, the circles give us the deterministic solution, right? And the green gives us stochastic, so we have just actually all sorts of different types of randomness in the system can drive this. We actually get this second impact early with the stochastic case, thinking of the d decreasing. We can follow the same sequence increasing. Again, the circles are our deterministic bifurcation figure, but we can also put in the stochastics, and again, we get a longer range of this second impact on the bottom that shows up. So even in the deterministic, there's a bistability, right? As we increase d, we get this 2-1 or bottom, top solution for a longer range. And then, of course, with the noise, we extend the range for that solution even farther, right? So there's all sorts of questions here in terms of what can we say in terms of bistability? How many solutions do we have to track? Are there other solutions that we should be tracking? And how robust is this to noise? Why should we go to one solution rather than the other? Okay, so I won't go a lot into bistability. I will come back to bistability at the end, but just to mention, I mean, we have 3 talks tomorrow that will not be necessarily focused on bistability, but we'll highlight different places where bistability can come up. For example, Dimitri will talk about compliant versus hard impacts with controls. Christina will talk about the influence of friction, and Rahul will talk about this targeted energy transfer setting where you also can see these types of behaviors. Okay. Okay, and all right, so let me get now into global, and so let me just, I've already mentioned a bunch of actually local analyses, bifurcation analyses, tracking also stochastic bifurcations and so on, Poincare maps. And there's very little in terms of global. I mean, there's some work using Lyapunov functions for the bouncing ball case, but that's really looking at the no bouncing case, right? In the energy harvesting, we're never in the no bouncing case because it's pointless. Okay, we need impacts on both sides for this to make sense. So we're never looking at that. There is work in the switching type non-smooth settings, but it's very different from impacting. We can do computational things in terms of basins of attractions, various computational methods, cell mapping, the path integration, but again, very expensive and not necessarily telling us the dynamical insight that we could get from a more of a global approach. Okay, now, of course, deciding to do global analysis is, either arrogant or completely naive. So I can, basically say I've never really been a great expert in non-smooth dynamics. Most of what I know from my postdocs, actually. So why not? Let's try it. Sure, we can do that, right? So it's probably more about being naive. But the big problem is, of course, that we have these transcendental non-smooth maps. Do we have a hope to get a Lyapunov function from that? Not really. We may have a hope to get one in the square wave case because things simplify down, but in the harmonic case, not so great. We have, multiple variables to deal with and so on. But okay, let's do a warm-up problem, right? So the warm-up problem is going to be not the bistable case, but just let's see if we can reproduce this sequence of bifurcations of a 1-1 alternating type behavior, period doubling to chaos, okay? And I've actually just circled here the branch on the top, the positive relative impact velocity to track. And you'll see in a minute why I'm only tracking one, because we're actually going to think in terms of return maps to a particular side of the of our impact oscillator, right? So, you know, within that, of course, from the global point of view, there's, you know, lots of transients, there's various basins of attractions, again, very noisy and complicated. So that seems kind of a little bit hopeless from that point of view. But I would say it's actually hopeful because we actually have impacts, right? And the impacts actually give us a basis on which to build very simple building blocks from which we can come up with new types of maps that help us to understand return maps, which help us to move towards the global dynamics. All right, so I'm going to eventually get to global dynamics down here. I'm going to have to take you on a detour to get there. And but eventually I will get to an auxiliary map that gives us global dynamics. But the first thing we have to do is look at different types of return maps. And so for that, we'll focus on just one side of our oscillator, the bottom. That's mainly because we have it tilted up. And so the ball does tend to return to the bottom relatively frequently. So that kind of makes sense. Okay, so let's first look at these simple building blocks and go from there. Okay, so we're going to think about first return maps just back to the bottom of our cylinder, right? So we can think about any of our sequences in terms of just these small building blocks where either the ball hits twice on the bottom. This is just in the time series again, or it can go from the bottom, hit the top, and come back. And pretty much everything else is built up with sequences like that. Now you could say, well, we hit a few times on the top. Again, because I have a little bit of angle here, that's going to happen very infrequently and be very transient. So we could track it, but just for simplicity of presentation, I'm not going to because it doesn't really change our results. Okay, so we'll look at a very small number of impacts and ask if we start in our state space is impact velocity versus impact phase. Impact phase is, of course, the difference between the impact location and the bottom of our oscillation. We can say, okay, if I start at this impact velocity and this impact phase, do I hit the bottom again, or do I go to the top and then come back to the bottom? And that we can completely divide our state space. And so the pink here is when we go bottom to top to bottom and come back. The black is just going bottom to bottom. There's a little blue patch in here. That's still bottom, top, bottom. We'll see in a minute why that blue patch is highlighted. But basically, we have the pink and the black. And that's it. We have two different return maps, just one that hits the top and one that doesn't. Okay. And any of our sequences, we can just put those together and we'll have those maps. So then what do we do with these return maps? This region just tells us the type of map that we have, but we actually need to know what's the next step in order to repeat that map over and over again. So we need the return map. That's going to be in 4D. Here it's drawn in 3D, right? So we have impact velocity, the resulting impact velocity after I start with a particular initial condition, and also the impact phase on the next step. So here you say K plus 1. I start with K. On the next step, it's K plus 1. Okay, and we can do that. Here I've actually shown this in a fixed phase and just seeing what that curve looks like if I project into the phase plane for my next impact velocity, let's say, versus the initial one. So we get these different curves. The pink curve, again, corresponds to the case when we go to the top and then return to the bottom. And then the black is just where we just hit the bottom twice. And so we can do this for each impact phase in state space. And that's how we get these 3D curves, which are the surfaces. So this is essentially saying this is the surface for my next impact velocity. These are the surfaces for my next impact phase. All right, so we just get a bunch of 3D surfaces that tell us our return maps. Now, you could look at this and just say, you've just made the problem a lot worse. Okay, we at least knew what was going on with our maps before. They were going from the bottom to the top and so on. Like, okay, this is bad, right? So yeah, it is. So, and maybe to make it look even worse, we now project it into the phase and see if we can see anything that's going on, right? So I've highlighted a few regions here, and basically these regions are highlighted because maybe you can see it here. There's a red diagonal through. This is the projection onto the phase space. So this is phase space for impact velocity, phase space for impact phase. And so there's a few like green and yellow things here. So why am I showing the diagonal? Because those are places where we could return to almost the same value that we started. That's why the diagonal is there. And so we could have potentially attracting dynamics here, but there's also features about these regions, even near the diagonal, that tell us we have potentially transient dynamics as well. So the question is, can we divide those up? If we really have to combine these two and go back to the surfaces and say, you know, how sharp are these surfaces or how flat are they? Because that actually tells us something about whether we have potentially attracting or transient dynamics. So it's a little bit hard to see from here, but maybe just to say, why should we care about that? Let's remember like our, dynamics course studying logistic map, right? So if we study just like 1D phase space using, let's say, a cobweb type analysis, we have our map, right? If our map crosses the diagonal, we have potential for a fixed point. If we have, for example, logistic map have the right value of R, we follow our cobweb to the map, to the diagonal, to the map, and so on, we'll cycle into that fixed point. But if the R is too large, we have a sharp slope here, then we'll just get chaotic behavior with that cobweb analysis. And then we can get, of course, in between period doubling and so on for intermediate values of R. So we'd like to use this idea of a return map idea in the background with the cobweb analysis here. So tracking the diagonals and tracking slopes and so on, something we're going to bring over to this higher dimension. Okay, so I found these simple building blocks. I found the return maps. All right, so now the question is, can we somehow divide these into these first return zones and say something about a composite map over these regions? All right, so just to remind you, okay, we have these return maps in 4D, but they're really based on just two simple maps going from bottom to bottom, bottom, top, and return. And so we're going to approximate these with some polynomials in order to have closed form expressions. Those will be useful later when we actually look at the global dynamics. Not absolutely necessary, but does help us to get a little more handle on what's going on. So, can we do that? Actually, these are pretty messy. Can we come up with some sort of polynomials? So before showing you that, I'll just say the answer is yes. With some care, actually, we do have to divide the state space up a little bit more in terms of approximating those. But this is just to show you that we can actually do this and it gives us something reasonable. So this is showing you the result. I'll show you how in a minute. So we come up with a composite map. We have polynomial maps on these 5 regions of our state space. And this is the original bifurcation diagram. Remember, we were tracking this upper branch of our bifurcation diagram for impact velocity, impact phase. This is the original variables, and this is our approximation. Our approximation variables will be V and phi. Right? So they don't, it's not a complete reproduction, but it's actually quite a reasonable approximation. Okay, so let's see a little bit what these maps look like. So for example, we can look in region. So region 3 here is small impact phase, small relative velocity. That's where we go, just hit the bottom more than once. And we can look at these curved surfaces and say, can we approximate them with polynomials? Yes, we can. They're ugly, but okay, this is where the computer assisted part comes in. We can get those relatively simply. And in fact, we can get the coefficients in these as a function of the non-dimensional length or bifurcation parameter D. And you'll notice here, these are polynomials in two-dimensional, both in phi and v. Okay, so that's one. In our other region, we're going from alternating bottom, top, bottom. We've actually divided this into 3 pieces. I'll show why in a minute. One of the regions, this blue region I had highlighted earlier, is actually a region near the diagonal where, because of the shape of the surfaces, we actually have a very likely return to that region. So it's kind of our likely attracting region. So we've highlighted that. The rest of this region is actually transient. We can see that a little bit from when we get away from this region, we see very sharp slopes and so on. Also, we're maybe away from the diagonal. So there's no reason to think that these regions are going to be attracting. So these are more of our transient type regions. So we start to see some of that already. We can actually go a little bit further, and even in these very transient regions, we actually reduce our approximation from a full 2D polynomial into a 1D or single variable to, let's say, coupled 1D polynomials. We don't have to do that, but it actually simplifies our analysis, helps with some of our phase plane analysis. And so we see here this green is just a curve approximating a whole surface, which obviously a pretty big approximation, but it does actually quite well, and it actually decouples these approximations, which makes things a little bit cleaner. But again, we don't have to do that. All right, so anyway, that gives you a little bit of the flavor there. I won't go into that in great detail, but it does lead to an algorithm, right, where we basically break down our phase space into our simple building blocks. Then we ask, can we approximate, we get the maps, we get these surfaces, and we ask, can we approximate them with these polynomials? If yes, then okay, we're done. But if no, maybe the surface is too complex. Maybe our approximation is not accurate enough. We have to go to a higher order polynomial. We come back and repeat this until we have a good approximation for the surfaces. And so actually we start out with really, 2 regions, pink and the black, and have to break this down into a few more just because of the highly irregular shape of these surfaces. But otherwise, we can do that. So we get a sequence of 5 basically different maps on these 5 different regions. We put them into a composite map M, and then we can reproduce D dynamics. So that basically gives us the composite map that we started with our building blocks. We have a composite map. Now, let me just go very briefly into the cobweb analysis, not because it's very clean, and I know it gives Danielle a headache every time we look at it, but at least it gives you a flavor of how we get to the auxiliary part, right? So now we've taken our basically 4D, we're projecting it down into the, our maps in the phase space for our approximate impact velocity, approximate impact phase. Now this looks kind of a mess. Everything overlaps because we projected it, right? So how do you actually follow these maps? And on top of it, in 2 of these regions, we have 2-dimensional maps. We can't draw curves. In these couple of regions, the 2 and the 4, we actually have lines because we did this approximation just with a single curve. But actually, you can read this because we'll apply the map for region N when both the phase and the impact velocity are in the same region. So we start out here in region 3. Okay, we do our cobwebbing. Eventually, actually, it's the phase leaves region 3. Region 3 is the purple, actually, light lavender here. Moves out, and suddenly it's not in region 3 anymore. So we have to say, okay, what region are we in? Well, we're still at that step where we have an R4 and we have an R4. So we can now use region 4 and follow that map. And then that shoots us over to where we're both, we have both the green line. So then we're in region 2 and so on. So, okay, it takes a while to figure that out. But basically there will be a unique in each step overlapping region that you can then say, we're in this region, we apply this map. And now you can see this down here. What I've just outlined is the orange line here, and actually the green is the exact. So it doesn't reproduce it exactly again, because we've done some pretty extreme approximations, but it's getting us the type of transient type dynamics that we need. And we're really, at the end of the day, interested in what are the attracting regions. So we can do a little bit better if we want to, but not always necessary. Okay, and this is just to say, actually, in this case, if you stare at this, you can see things actually cycle into a fixed point down here. So that's actually here, the blue line on our bifurcation diagram, so larger values of our non-dimensional length d. And we can look at other values, for example, smaller d, where we have period doubling. We see we get that from this attracting little square in the phase space, again, with the cobwebs. And then we can even look at the chaotic region, and we get this chaotic behavior, reproducing this bifurcation sequence. Okay, so our cobweb analysis is there. We have the composite map, but at the end of the day, I said we're interested in the regions. What are the attracting regions for our impact velocity, impact phase? That's going to give us our energy. Okay, and so, I mean, the cobwebs have sort of told us here, but that's just the cobweb analysis. It's actually not the really demonstrating that this is our attracting region. So we go through our auxiliary maps, and this kind of explains why we work so hard for this crazy cobweb analysis where everything is overlapping, because the cobweb analysis really helps to motivate the auxiliary maps. So the auxiliary maps actually motivated by this idea, like, let's get out of these two-dimensional surfaces that we can't see in the phase space because they overlap each other. Let's actually break things down into two 1D maps. And how do we do that? By actually taking the max and the minimum, the bounds on these maps for the impact phase and the impact velocity. So this is just the example. It's just, kind of a horrible mathematical expression, but basically it says for the impact phase, let's take the maximum of over V, the impact velocity, and then just get the max and the min for the phase from that, right? And so that's basically this, the blue and the orange curves here give us the upper bounds on the map for the phase. And we do the same trick with the impact velocity. So we're essentially going to be bouncing around between these upper and lower bounds rather than going to any particular map or curve, all right? And in some cases, actually, these expressions can be written directly in terms of these polynomials that we have. In some cases, the max and the min mixes everything up, so it's not quite as clean. But anyway, but now we can do our cobweb analysis in this auxiliary upper and lower bounds. So after, sort of wandering around, we get into this region where we have the upper and lower bounds. And essentially, we come in with our cobweb, we hit the maximum, we drop down, then we hit the minimum and go back and forth. So of course, like if we're looking for a fixed point, we're never going to get to the fixed point that way because we're always going between the upper and lower bounds. So how do we actually get there? Well, after we get the some attracting, let's say, square from going back and forth between the upper and lower bounds, that's like our new bounds, right? So these orange lines here actually show a zoom in, so we can actually restart our auxiliary map with a new bound given by the limit of this red box. So we zoom in and then we repeat with our new bound. So in this case, the box keeps getting smaller and smaller. We're zooming in each time. And here the last zoom in is down in this little tiny little black box. Then we zoom in according to the orange line. So these, the range here is very small. And so we get a tiny little box here as our attracting point. So it's never really a fixed point, but it can be very, very small. And that's actually really what we're interested in. We're interested in the region where the impact velocity, impact phase are going to land. So that was our fixed point case. And so we can track as we zoom in and get smaller and smaller, the size of this region actually goes down to essentially 0. This is the fixed point case, but you know, we also have these period doubling and chaotic cases. And there we actually see that the boxes never shrink down to 0. They shrink down basically to the size, the range of the values we get for these regions. And we do have a little bit of shrinking here, but in the end, we get some just attracting period M cycle for these attractors. Okay. So this is really the repeated application of this auxiliary map is really what gives us the size of the attracting region. And that comes back and gives us the range of our impact velocity, which then in turn tells us where is our energy going to be, all right? And because we've done this in the setting of maps across the whole state space, we actually have global attraction for this example. Okay, so that was the warm-up problem. So let's now try to go to the real problem. Okay, so just to remind you, what have we done for the warm-up problem? All right, so we have these basic maps, just 2 maps. And actually, just to remind you, these are not Poincare maps, they're not periodic. They're not even kind of, you know, using exactly the same sequence. One goes back and forth, one just stays, whatever. But it makes sense for the impact oscillator. And then, you know, after going around to this sort of geometric path, we end up with our global dynamics through this auxiliary map. Okay, and that gives us these sequences and the implications for energy. So let's just go and look very briefly at the bistable case. So I'm back to this case where we decrease or increase DC, the bistability of our bottom top or a 1-1 solution, or hitting twice on the bottom, once on the top type solution. And of course, the stochastics that can extend the range of this. So what we'll see using kind of similar approaches, not only insight into the bistability, but also insight into the stochastic influence. Okay, so we play exactly the same game, except now my building blocks are not just bottom to bottom, bottom to top and bottom, but also hitting twice on the bottom, once on the top, back to the bottom. But we can write down maps for those as well, return maps. And probably not surprisingly, in between returning to the bottom, hitting the top, we have a whole region in these red dots that are where we go to twice on the bottom, then to the top and return. Okay. And this is the case when my D is large enough so the just back and forth solution is stable. That's given by this little star here. So now let's change D and follow this bifurcation sequence. So as we do that, this region of the twice on the bottom, once on the top gets larger. The bottom, top, bottom solution region kind of, hopefully you can see that here. There's a little green piece that looks like Baja California that's kind of sticking out here. And it's kind of getting encircled by the bottom, top, bottom. But that's exactly where this attracting solution is living, right? So in fact, already looking at these maps, we can see why this solution is getting very sensitive to noise, because it's sitting here basically surrounded by other solutions in a very small region. Now you could ask, well, maybe it's a very highly attracting region. What does it actually look like? And that's where looking at the shape of the maps associated with these regions actually makes sense. So I won't drag you through all of that, but we can do the same sort of trick where we project onto our phase planes, look at what's intersecting with the diagonal as potentially attracting regions. So here for the bottom, top, bottom, this is for this larger D, we see these intersections turns out to be attracting. We can look at the contour maps for that. or the 3D surfaces, it's actually in this little valley in green here, if you can see that from the surface. And if we look at the case where we hit twice on the bottom, top, and back again, we only have one solution that impacts, or one surface that's impacting the diagonal. We actually would need two for this to be a fixed point, right? Because we have twice on the bottom in that solution. And the second one is nowhere near the diagonal. So already this projection is telling us we don't have bistability. But as we change D, these things start to collide. And then suddenly we have two intersections for the bottom, bottom, top, bottom case. So potential for an attracting solution, we have to look at the surfaces. And in the meantime, the other solution, just going alternating bottom and top, still intersects with the diagonal, but if we look more closely at the surfaces, there actually is no attracting solution there. So this is already telling us that, you know, how we lose that one solution and gain the other one. And even further than that, if we look at the surfaces associated with the phase, as D changes, we lose this attracting solution. It's completely cut off. Plus the slope of this part in the middle for a phase is very sharp. So that basically says that if we have any sort of noise, the noise cannot push us to larger phase. It has to push us to smaller phase. Okay, why does that matter? That matters because this is how we get the bifurcation from going alternating bottom to top to hitting twice on the bottom is with the smaller phase. And if we zoom in, this is actually showing both solutions. This green is zooming in. Maybe you can see it here. The black is the alternating bottom to top. The red is actually hitting twice on the bottom here. And it actually has slightly, very slightly, but enough to create this bifurcation. And so even small noise will push us, can even push us out of this into this hitting twice on the bottom, so different types of solution. So this already gives us an insight into the noise sensitivity in the problem, and we haven't even done the full auxiliary maps or anything like that. But anyway, so this gives you an idea how this, looking at these problems from this building block point of view, tells us a lot about the basically the noise sensitivity and various attraction by stability of the solution. Okay, so hopefully I've given you something to think about in terms of throwing out, I shouldn't say completely throwing out, but not using our constructing solutions, but instead thinking in terms of other types of building blocks to track both transients and attracting behavior, building these composite maps and the auxiliary maps for the global dynamics, giving us insight into all possible solutions that we have and their attraction, which of course has impacts for our energy, bistability, and noisy transitions. So thank you very much.